Text generation using different recurrent neural networks. What is text generation? Natural language generation is the process of deliberately constructing a natural language text in order to meet specified communicative goals. Text generation techniques can be applied for improving language models, machine translation, summarization and captioning. Automatic text generation means new text is generated automatically by deep learning the given text. RNNs. RNNs stand for Recurrent Neural Networks. In basic neural networks, it is assumed that inputs and outputs are independent of each other, but in real-life applications, we sometimes need to know previously computed output for current computations, so RNNs solve this problem. As the name suggests, recurrent, which means they perform same task for each element of sequence of input. RNNs are the networks that have loops in them. Here xt is input which is going into RNNA and ht is output which is going back into it to act as current input. RNNs work very well for sequential inputs, but they have a problem of vanishing gradient, which means the gradients of the network's output with respect to the parameters and the early layers become extremely small. It depends on the choice of the activation function. So to solve this problem, LSTM arises. LSTMs. LSTMs stand for long short-term memory. These have memory cell which solves vanishing gradient problem of RNNs. The memory cell have three gates called input, output and forget. It also has self-recurrent connection. The input gate allows or blocks the incoming signal to change the memory cell state. The self-recurrent connection ensures that the memory cell state remains constant from one time step to another. It has 1.0 weight and it also avoids any interference from outside. The output gate allows or prevents the effect of memory cell state on other neurons. The forget gate allows the cell to remember its previous state or forgets it according to its need. GRU. It is similar to LSTMs as both were designed to solve the problem of vanishing gradient. It has less complex structure as compared to LSTMs. A GRU has two gates, reset gate and update gate. The reset gate tells how new input will combine with previous memory. The update gate tells how much previous memory will be kept around. To achieve simple RNN model, we can set reset gate to 1 and update gate to 0. Problem statement and objectives. Problem statement. The techniques which have been used for text generation including Markov chains (MEC) and hidden Markov models (HMMs) are insufficient to create whole sentences. RNNs have been implemented for text generation, but Tensorflow library is not used. Objectives. To develop text generation system which deep learn one text and then generate new text using recurrent neural networks. To train RNN, LSTM and GRU for developing language model. To compare the results of different models to conclude which network perform well in task of text generation. To use Tensorflow library. Tensorflow. It is an open source library developed by Google. It is used for numerical computations using Dataflow graphs. Nodes in this graph represent mathematical operations and graph edges represent multidimensional arrays called tensors. It is similar to NumPy. It first builds graph of all the operations that are need to be done, then calls a session which run the graph. Placeholder. It is a way to feed data into a graph. FeedDict. It is a dictionary to pass numeric values into graph. Block diagram. Input text is first pre-processed, then model is built. After that, sampling of text is done and finally output text is generated. Datasets and pre-processing. We have collected 5 different datasets of different sizes. We have collected Shakespeare work, War and Peace book and Harry Potter series. Input data is first pre-processed, which includes tokenization, removal of infrequent words. Tokenization. A token is simply an instance of a sequence of characters that are grouped together as a useful semantic unit for processing. Pre-processing. First tokenization of text is done. Then removal of infrequent words. Then vocabulary and inverse vocabulary formation. Then batches are built. Removal of infrequent words. Training depends on the vocabulary size, so removal of infrequent words will avoid our vocabulary to be of large size. As we don't have many examples of those words, our model would not be able to learn how to use them properly, so they are removed. Vocabulary and inverse vocabulary formation. Vocabulary is formed in which each word is mapped to index based on sentences. Inverse vocabulary is maintained in which there is index to word mapping. Model building. First initialization of variables is done. Then graph is built. Then forward pass and finally training session runs. Initialization. The first step is to initialize the variables. Creating computational graph. Batch data is fed into placeholders. These placeholders are start nodes of the graph. RNN state is also fed into placeholder. This state is output of previous run. The Tensorflow variables are weights and biases of the network. These make Tensorflow to be persistent across all runs. These are updated for each batch incrementally. Forward pass includes building part of the graph that does actual RNN computation. In this we concatenate two tensors. Run training session. A session in Tensorflow is executed. Data is generated on every epoch. Here first thing is 250/8100. 250 is batch number currently running, 8100 is total iterations. Then epoch number. Then training loss. Then time taken to run each batch. Checkpointing. It can take hours, days or weeks for deep learning model to train, so if it gets stopped unexpectedly we can lose our work. The network is slow to train because of requirements of optimization. So we have used model checkpointing to avoid this issue. In this state of system is maintained in case of failure. It record all of the network weights to a file each time, and improvement in loss is observed at the end of the epoch. Input data. This data is taken from book called War and Peace. This text is of about 1.7 MB. This is output for RNN. So the first line is, he was evident he could not be familiar. We can see that output generated is not realistic. This is output for LSTM. So the first line is, he had no last definite barrier. We can see that it is better than the if RNN. This is output for GRU. So the first sentence is, he could not have been in a constant state. We can see that it is quite better than both RNN and LSTM. Plot between training loss and iterations for input data 1. We can see that training loss is minimum in case of GRU, as iterations are increasing, loss is getting to almost zero. Plot between training loss and iterations for input data 2. We can see that training loss is minimum in case of LSTM. Plot between training loss and iterations for input data 3. We can see that training loss is minimum in case of LSTM in early iterations, but after that GRU has minimum loss. Plot between training loss and iterations for input data 4. We can see that training loss is minimum in case of GRU, as iterations are increasing, loss is almost to zero. Plot between training loss and iterations for input data 5. We can see that training loss is minimum in case of LSTM, then RNN and then GRU. So loss depend on input text data.